Okay, here we go. It's the same old Wamini. It's always the same students who are sitting there looking clever. Welcome to all the students. It's very nice to see you. So, like I said, last energy lesson, last enthalpy lesson on the fourth of the topics which we have to cover in energy. We are going to do a stop blowing kisses at me, Wamarini. Um, what we are going to do is we're going to do look at a question about a practical, something that comes up in paper 3, and I showed you it briefly last time. And then at the end we will do some more calculation questions, probably Bendomexo ones, because they seem to be the ones which were causing the greatest problems. So first things first, I'm going to start by sharing my screen and showing you what the question was that we looked at that looks quite difficult and has some techniques that we need to know about. So here we go. So I hope. Okay. This, hang on, let me just, come on. Right. This was the question, and it's quite a big, quite complicated looking question. But by the end of today, I hope you will be able to do this question and score almost all of the marks. I asked you to read it last time, and it tells you that we have a plastic beaker, we put some water in it, and then we add some sodium hydroxide, and at various times, every half a minute, we take the temperature. So the temperature at 0 time was 15, but when we added the sodium hydroxide, it started to heat up. Now, because it was heating up, it means it was an exothermic reaction. So it goes 15, 21, 29, and so on. And then it starts to cool down. And the first assumption that you might make, you might think, is that the maximum temperature it gets to is 29. And I'm going to remind you why it's not 29 and why it's actually 32. I'm going to show you it again. But this is a very typical question. Plot the graph. From the graph, find the maximum temperature. Find the temperature change. Calculate the moles of sodium hydroxide. And then the biggest part is part 5. So part 1 is probably worth 2 or 3 marks. Part 2 is worth 1. Part 3 is worth 1. Part 4 is worth 1 or 2. Part 5 is probably worth 3, maybe 4 marks. So it's the last one is much more difficult. So what we're going to do is I'm going to go back a bit and we're going to look at how we do this sort of type of calculation. So I'm going to write some bits and pieces. I'm going to ask you to look at some bits and pieces. We're going to start very simply. I want to ask you first, how many of you are happy with what specific heat capacity, 4.18, of water means? How many of you are happy, not too sure, or unhappy? So, Wamoini, a bit of a mixture. Dandora girls, happy with specific heat capacity, unhappy, cool, Silver Spring, not so happy, Glory? Okay, that's good. Okay, so I'm going to go through it very briefly then, that part, and I'm going to hope that these calculations are mostly fairly simple, and then I'm going to allow you to have a go at that question, okay? So, here we go. I'm going to start with a different, oops, come on. I'm going to start with a different, come on, slide, and I'm going to just look at what specific heat capacity means for those few people who weren't sure. So for 1 gram of water, which is the same as 1 cubic centimeter of water, or 1 mil of water, they're the same. 1 mil and 1 cubic centimeter are defined slightly differently, but they're essentially the same. And because the density of water is 1 gram per cubic centimeter, then 1 cubic centimetre of water is 1 gram. So for 1 gram of water to get 1 degree Celsius hotter, it takes 4.18 joules. This is a very, very well-known piece of information. So if we want to take 1 gram of water and make it 2 degrees hotter, then it will simply be twice as much. Okay, so if you're not sure about this, it might be worth writing down some little bits. I will send this PowerPoint to your teachers or supervisors, but this is what it's all about. So specific heat capacity is this, that for heating 1 gram of water to 1 degree hotter than it is at the moment, we need to use 4.18 joules. And they will always give you this in the question. Okay, that's really easy. So if I take 1 gram of water, but I make it 2 degrees Celsius hotter, then it would have to be just twice as much, 8.36. Real simple. The similar sort of thing is true if I change the volume or the mass of the water. So if I take, okay, let's have 5 grams of water and make it 1 degree hotter. So you have to always spot the volume or the mass of the water and the temperature change. So now instead of 4.18, it will be 5 times 4.18, which is 20.9. So if you want to write that down, just as a simple way to remind yourself, that's not a bad idea. Okay, so that's how the specific heat capacity works. We can make it more complicated. So let's say we have 3 grams of water and it's 10 degrees Celsius hotter. Then many of you will know, you can have a go and work it out yourself just now. If you want to just check your arithmetic, what would the energy be required if it is 1 gram, 1 degree is 4.18? Then if I make it 3 grams and 10 degrees Celsius hotter, how much would be needed? How many joules? Get a calculator and quickly calculate it just to make sure that you're doing the right thing. Just take a moment just to do the calculation yourselves. Because if you can do that, if you can do all those, then if you can do this really simply, that's great. Oh, Glory can't find their calculators. Can't Glory, do the calculation, please. You should have a go at all of these things. They're just practice. Show me a little bit lower, please, Glory. Aha. So it will be, very good. So it will be 3 times 10 times 4.18, which is 125.4. 125.4. Show me if you got that right. 125.4. Who got 125.4? Come on, Glory. Get your calculators out and start to do it. Well done, Wamuini. Well done, Silver Spring. Well done, Dandora Girls. Very good. Capiro, we can't see you, but it doesn't matter. I hope that you got 125.4. Okay. So simple stuff so far. So here it is. Okay. Now it depends. The specific heat capacity is not constant for different substances. So for instance, for copper, the energy required is 0.39 joules. So copper is easier to heat up. So if we have 10 grams of copper and it's heated up by 5 degrees, what will the answer be? If the specific heat capacity is 0.39 and I have 10 grams of copper and I want to heat it by 5 degrees, what will the answer be for the energy required? It's simple. This is basically just physics, but it's where chemistry and physics just cross over. So let's have a look, just have a quick calculate. We've got an answer from Dandora Girls, which is very good. Excellent. We've got a calculator. We've got a calculator in one of the sentences. It's a good way of doing it. So it's going to be 10 times 5 times 0.39, which is 19.5, which everybody got, which is excellent. Well done. Now, what happens here? Oh, sorry, I've just got to move something. Oh, come on. I can't get rid of one of my screens. Sorry, I've just got to get rid of one of my screens. It's in the way for me. Okay. So what we call the energy required to do a particular piece of work is Q. Sometimes it's capital, sometimes it's not. And the mass of water heated is M. The energy needed to make 1 gram of the substance 1 degree hotter is called the specific heat capacity, which is sometimes given the letter C, and the temperature rise is delta T. So Q is M, the mass of water, not the mass of all of the chemicals, just the mass of the water, times the specific heat capacity of that substance times the temperature rise. So if it was copper, it would be different from water, but most of the experiments which you will come across will be about water. Okay, so Q equals M times the specific heat capacity times delta T. So the specific heat capacity, I said, is sometimes given the letter C. There's no need to remember that it's C, but that is the specific heat capacity. Okay, so Q, the energy required to do whatever it is M times C times delta T. There. That's what you need to know. But often, as we saw in the question which I showed you at the beginning, it asks for the molar heat energy or heat or enthalpy change. And that means that we need the number of moles of chemicals reacting. Now, this is what I want you to understand, that Q can be just the amount of heat. So if you look at the sun heating a puddle of water or a stream, then you could calculate it like this. The amount of heat that goes in is equal to the mass of water times 4.18 times the temperature that it rises, and that will tell me the energy. It will tell me the energy that I need to heat anything, a pan of water, a swimming pool, the ocean. It doesn't matter. That's like that. But in chemistry, we're interested in moles. So here is a little bit about moles. Now, I'm going to assume you understand what a mole is. So I'm just going to come and ask and make sure. So how many of you are okay with moles, maybe okay with moles, not okay with moles? Wamuini, Dandora, Silver Spring, just show me. Glory, not very happy. Silver Spring, not very happy. Dandora, maybe okay. Wamuini, lovely face, great. Okay with moles. Okay, so I'm going to assume that most of you are okay with moles, but not great. Don't worry if you're not very good with moles, Silver Spring. We will teach you about moles of Liverpool Football Club next time. But today, what I'm going to do is I'm just going to go with understanding what a mole is. The first thing is that a mole is only a number. Hello, Mathari. Nice to see you finally. The mole is simply a number. 600,000 million. That's 6 times 10 to the 23. So if I have 6 times 10 to the 23 of anything, it could be a cup. I could have 600,000 million cups, and that would be a mole of cups. I could have 6 times 10 to the 23 hairs, and that would be a mole of hair. But a mole, yes, and some of you got a lot of hair. But in chemistry, we talk about moles and MR and AR, that's RMM, and so on. So what we're going to do is now we're going to assume that we understand enough about moles just to do this little bit. So here we are. I'm going to go back to screen sharing. So if it tells you that 2 moles of ethanol burns and gives out 2 0.734 kilojoules, then to work out it per mole is the important thing. Now that's obvious, because if I have 2 moles and it produces 2,734 kilojoules, then all I have to do is to work out 1 mole, and that's 2,734 divided by 2. So it's 1367. But because it's burned, the heat will be given out. And you should remember from last time, if you were here last time, that an exothermic reaction has a negative sign in front of the kilojoules. That is because the heat is lost from the chemicals. In other words, the delta H for this would be negative 1367 kilojoules per mole. It doesn't matter whether you write kJ/mole or kJ mole to the -1. It means exactly the same thing. It means kJ over moles. Okay, so just look at that again. If we have 2 moles of ethanol is burned and it gives out 2734 kilojoules, then 1 mole would give out half of that. But the delta H will be negative 1367 because when ethanol burns, when alkanols burn, they give out heat. Simple. Okay. So delta H is Q, and if you remember, Q is mc delta T, the mass of the water, only the water, times the specific heat capacity of water, 4.18, times delta T over the moles in the reaction. That's something you have to remember. Now, moles in reaction are often called N, so it would be Q over N. This is a little simple experiment. You might get this in paper 3. In paper 3, when you have to do a practical, you might easily get one of these. They have given it before. In this, you would get instructions which would tell you to measure out a certain volume of water, put it in a cup or a beaker, put a thermometer in, measure the temperature, and then every 30 seconds, measure the temperature again, having added some chemicals. They wouldn't normally give you sodium hydroxide because it's too dangerous, but they use sodium hydroxide in theoretical questions. So you mix it like that. It's not a great system. A much better system would be one like this. This is a way of taking all the heat from a little spirit burner. We are burning something like an alkanol in the bottom here. It is burning. This is a funny shaped beaker with a gap at the bottom and a little copper tube which goes up through it, and air is sucked out through it. And the heat from here goes through the copper pipe and transfers the heat to the water, and the thermometer takes the temperature. Don't bother drawing it. This is just a better version of something like this. Something like this is very simple. There are errors, but they're not that bad. This is just a lot more perfect. Okay, so going back. So if the energy required in a reaction is mass times the specific heat capacity times delta T, and the delta H is Q, that's mc delta T over N, then that's how we work it out. So we would need to know the amount of water in here. Then we would measure the temperature change. We would know the specific heat capacity. We would work out Q, and then we would see how much chemical we had added. Same here. We would see how much had burned by weighing. All right. So here is a calculation. I'm going to give you a chance to have a go at this first. Before I do it for you, I'll show you it. But I'm going to give you a chance for you to do it. So it says 0.600 grams of propane was completely burned in air. The heat evolved raised the temperature of 100 grams of water by 64.9, and the specific heat capacity is 4.18. So you should all be able to work out. So this is like this one here. So the propane is burning here, and it is raising the temperature of 100 grams of water. So work out Q first, okay, the Q, and then try and work out the moles of propane. The moles of propane, well, you need to know the RMM of propane. Carbon is 12 and hydrogen is 1. So the RMM of propane is 36 plus 8, which will make it 44. But that's later. So do Q first. Okay, have a go. I'll give you 5 minutes in which to have a go at this and see how you get on. If anybody has a question, just write it and show it to the screen, and I'll see if I can help. Remember, Q is mc delta T. That's M, there's the mass of water, times this number here, 4.18, times delta T, that's the change in temperature. And then that is eventually all divided by the number of moles of propane. And moles is grams over RMM. Moles is grams over RMM. Have a go. You will find that because we're using joules at the moment, you'll get a large number. You can divide by 1,000 to turn it into kilojoules if you want. Anybody has the answer, you can show me it. Even just give me the answer to Q if you want to start with. That would be cool. If you want to give me, you want to show me Q. Good working. Well done, everybody. I'm very pleased to see people working. So work out Q first, then work out the number of moles, which is grams over RMM. The RMM of propane, because carbon is 12 and hydrogen is 1, will be 36 plus 8, which is 44. Dandora girls, have we got do we have an answer? Ooh. Show me again, please. Very good. What's your name, please? Lucy. Well done, Lucy. That's really good. Now you need to work out the number of moles and divide it by the number sorry, but that you've worked out Q. Now work out moles and divide the Q by the number of moles. Lucy at Dandora is first at the moment. Anybody else want to show me their answer for Q? Come on, Wamoini. Come on, Wamoini. Come on, Glory Secondary. Come on, Glory. Come on, be proud. You're good students, I know you are. So let's see some action. Let's find Q. Q equals the mass of water times the specific heat capacity, which is at the bottom, times the temperature rise. That's easy. It will give you a big number, something a little bit over 25,000 joules or 25 kilojoules. Okay, bit over that. Then you need to work out the number of moles, and then you need to divide Q by the number of moles. A little bit. Oh, no, the moles is not 6.98. That's the wrong way up. We need to go. The moles is the mass of propane over the RMM of propane. Okay, it's the mass of propane, which is in the question there, which is 0.600, divided by the RMM of propane, which will be 44. Okay, try that again, and then we'll have a look at the whole answer. I tell you that the moles will be less than 0.6, obviously. It'll be 0.01 something. So if the Q is about 25,000 and moles is about 0.01, your answer will be about 20,000. Sorry, 200,000. In about 1 minute, I'm going to do the calculation because some people will find it very difficult. So I'm going to do it so everybody can see how we do it. Okay. Then we can have a go at another one. Okay, here we go. So I hope a lot of you have got somewhere along this track. Let's see how we do it. So we always start by showing what we're going to do. So we go, okay, Q, that's the total heat change in this experiment at the moment, is M, that's the mass of water, not the mass of the whole thing, just the mass of the water which is being heated up. Oh, Amoini. Sorry, hang on. Let me just make you a bit bigger so I can see. Hang on. Show me again, please. Wamuini. Oh, well done, Dandora. I guess that's Lucy again. Wamuini. Sorry, show me again. Don't give up, Wamuini. Come on, be proud. Away just a little bit further away. Ah, okay. Up a bit. And down a bit. Oh, I think sorry, it disappeared. But anyway, let's go through it. It looks like it's about the right thing. I'm just gonna show you it now, everybody. Okay. So if M is 100 and C is 4.18 and 64.9 is delta T, always write it out like this. Then you will find that Q is 27,130 approximately. Okay, so there's the 100 grams of the water. C is 4.18. Delta T is the change in change in temperature. Then we need to work out the moles of propane which burned. We don't worry about the water now. So the moles of propane is the mass over RMM or MR. This is another symbol. MR, relative molecular mass, is the same as RMM. So it's 0.6 divided by 44, which is 0.01364. It's 363636. It doesn't matter. Okay. So then we say, okay, if the delta H is Q over the moles, then it is this 27,130 divided by 0.01364. And that gives me the answer of minus 1990 kilojoules per mole, or minus 1990000 if you had it in joules, but it should be in kilojoules. So you might have come out with a number 1990000 approximately. I came out with 1989401. Okay, that's what I got. And it's negative because it's burning. Now, Wamuini are going, whoa, no, don't like it. Okay, tell me why, Wamuini. Just unmute and tell us about it. Let me stop sharing and just ask everybody how many people get this, because we can go through it again. So, Dandora girls, did that make sense to you? Some sense or no sense? Thank you, Dandora. Silver Spring, did that make sense to you or no sense to you? It's okay, whichever one. Yes, okay, I will, Wamuini. Okay, Glory, sense, no sense. Some people sense, some people further back, no sense. Okay, Ezekiel, what are your team like at the moment? Wamuini were not happy about the bit from where we go from Q to delta H. So we'll go through that again. I'm going to share that whole calculation again. Okay, so here's the question again. And what we have to do is to find the pieces of information we need. So remember, Q is M times C times delta T. M is only the mass of the water. There it is, 100 grams of water. So M is 100. The specific heat capacity is 4.18, and the delta T is 64.9. It says it raised the temperature by 64.9. Therefore, Q is 100 times 4.18 times 64.9 is 27,130 approximately. I got 27,128, but it doesn't matter. It's only approximate. Then, to find delta H is this number here divided by the moles of the chemicals which are reacting. The chemical which is reacting is the propane, and propane, it says we have 0.600 grams of propane, and then it's a question of how many moles we have, because that's not moles. Moles is equal to grams over RMM. So we go, okay, it's the mass, which is 0.600 over 44. It's 44 because each carbon weighs 12, each hydrogen weighs 1, so C3H8 weighs 36 plus 8, which is 44. So 0.6 divided by 44 is 0.0136363636, and so on, which has been simplified to, approximated to 0.01364. This is the bit which people get confused over here. The bit which it says delta H is Q over the moles, Q over N. So It's the Q, which is the total amount of heat taken in by the water, divided by the moles of whatever it was that heated up the water. Okay, so that will be 27,130 divided by 0.01364. That will give me it in joules per mole. I need it in kilojoules per mole. So there we are. They've put the minus here, the negative here, because we know that it's heat given out. Okay, so it's exothermic, so it is lost. And that equals negative 1990. That 27.13 is this 27130. Yeah, to turn joules into kilojoules, divide by 1,000. Okay, I'll give you a moment to write that down if you want to. Is that better, Wamuini? No? Better. Ah, yes, okay. This is negative because at the end, we need to remember that this is propane burning. Because the propane is burning, it gives out heat. If it gives out heat, it's exothermic. If it's exothermic, delta H is always negative. Okay, cool. Excellent. Let's have a look at another question. Okay, here's another one. We're going to only do this one, then we are going to look at the whole process again. So in this one, we have 50 cubic centimeters of 1 mole hydrochloric acid added to 50 cubic centimeters of 1 mole per cubic decimeter sodium hydroxide. Temperature rises by 6.8, and the specific heat capacity is 4.18. Now, what you have to spot here is that we are adding 50 cubic centimeters to 50 cubic centimeters. So we end up with 100 cubic centimeters. 100 cubic centimeters will weigh 100 grams. So we're going to work out Q first. It will be the 50 plus 50 times C times delta T. And then we have to try to work out the number of moles of one or the other of the chemicals and divide by that. So we're going to work out Q first. Remember, it's 100 is the amount which is the amount of water which is in there. So Q is going to come out as about just under 3,000. If you've got something a bit under 3,000, then that's fine. I will then show you how to do the calculation of the number of moles if you don't already know it. Dandora, do you want to show me that again? Yeah, good. Excellent. Really good. Who's that? Not Lucy again. Chelsea. Well done, Chelsea. You're beating Lucy now. Wow, cool. Okay, so Chelsea has got the right answer at Dandora. Now she needs to try and work out the number of moles of hydrochloric acid or sodium hydroxide because they're the same. And I'll tell you that moles is equal to the number of cubic decimeters times the concentration. It's 50 over 1,000 times 0.1. If you're not happy about that sort of mole calculation, do not worry because we will do it next time. So in other words, the moles will be 50 over 1,000 times 1. That's an important skill. That moles is concentration times volume in cubic decimeters. If you can get the Q, that's worth 2 marks. If you can get the N, that's another 2 marks. So the total is worth 5 altogether. Don't worry if you don't know how to do the moles. I promise I will show you next time how to work out moles. But the answer to the Q is around about 3,000, just a bit less than 3,000. So hopefully you will get the right answer there. Not quite. No, no, the moles is not 76.5. We don't need the 76.5. What we need is the number of moles, Dandora, Chelsea or Lucy or whoever. And that will be 50 over 1,000 times 1. 50 over 1,000 times 1. I will show everybody that in just a minute. So I'm going to stop sharing just for a minute so I can tell you something about moles. Okay, so I'm going to just go to my other board. Oh, show me it, Glory. Show me Glory, please, Glory. Show me again. Glory. Some student showed me the answer there, I think, and I think you were right. I just need to see it, please. Yes. Now, if you can divide your Q by that, you will get the whole answer, which is really good. Okay, here we go. So this is what I'm going to show you, moles. Okay, I'm at the board here. I'm over here. So there are 2 different calculations of moles which are quite common. If it's a mass, let's see if you can see that. Yeah, just a bit too high. Sorry, I'll come down a little bit. If it's a mass, then moles equals grams over RMM. Okay, that is always true. That moles is grams. Let me just put it up a bit. Sorry. Grams over RMM. I'll just get rid of the light a bit. There. If it's a solution, then moles equals concentration times volume in cubic centimeters over 1,000. So in this example, we had the concentration of 1.0 and the volume is 50 over 1,000, and that will equal 0.05. 0.05. Okay, that's the moles there. With the propane, it was 6 over 44. And 6 over 44 was 0.01364, I think. Okay, that's how you work out moles. Moles, if it's a mass, is grams over mm. Okay, if it's a solution, then it's the concentration times the volume in cubic centimeters divided by 1,000. But we'll do that next time. Okay, so I will do mole calculations next time. All right, so let's go back to the calculation. Okay, so We work out Q equals mc delta T. M is 100 because it's 50 added to 50. C is always 4.18. They will tell you that. You don't need to remember that. And the temperature rose, in other words, heat was given out by 6.8. And therefore, that is 2842 joules, which Kelsey at Dandora got, and I'm sure many of the rest of you got. A bit more complicated is the next bit. You have to remember that delta H is Q divided by the moles. The moles of what? Well, in this case, it doesn't matter because the hydrochloric acid and sodium hydroxide react together 1:1. So either one of them is okay. The moles of the HCl is the concentration times the volume in cubic decimeters, which is 1 times 50 over 1,000, which is 0.05, which somebody at Glory got, which was excellent. Now, delta H would be that 2842 divided by 0.05, and then divided by 1,000 to make it into kilojoules. Now, the moles of the sodium hydroxide works out the same, so we could take either of them because they react 1:1. So it doesn't matter if we have HCl or NaOH, it's the same number of moles. Therefore, delta H is the joules divided by 1,000 to turn it into kilojoules. That's negative 2.842. There's a 2842 becomes 2.842, and it's negative because it is given out, because the heat is given out, so it's exothermic, divided by 0.05, and that's negative 56.84 or something. We call it negative 57. Okay, so hopefully that makes a bit more sense now. Okay, I'm going to look at another question. This is one which was used in a KCSE examination paper 3. Okay, in a paper 3, and this was one where people had to do it. We're not actually going to do it now, but I'm going to show you how it works. So you have 100 cubic centimeters of copper sulfate solution. So we assume that the water is 100. Don't worry, we're not going to do it yet. Don't bother doing the calculation unless you want to. 100 of the of water times 4.18 times 25.1. I'm going to tell you that the magnesium is an excess, and therefore not all the magnesium will react. So it's about the copper sulfate, so you have to work it out with the moles of the copper sulfate. I will send that to your teachers, but we're not going to do that right now. Okay, we're not going to do that one right now. So what we're going to do is we're going to look back at the question from KCSE. So this is what we have to do with this one here. This is the one, this is an actual KCSE question. And we're going to have a quick look at this now so we can see the other skill you have to be able to do. So here it is. Firstly, it says draw the graph, and then you have to remember to extrapolate, which works out what would have been the temperature if it was not cooled down by the air. So you draw the graph. I did it with Excel, so it's not a very nice graph. You would get, you might get marked down because it's not very good. The point is that it goes up from 15 up to 29, but it only goes up to 29, and it should have gone higher. It should have gone higher because it is being cooled down by the air in the room. How we find how much it gets cooled down is using this. So this is a skill you need to be able to do. This is drawing a line back through the cooling down area. Look, from 29 it goes 29, 28, 27, 26. We draw a line, continuing that line back until it's above time 0. That's what we call the extrapolation. Now the total temperature change is from 15 up to whatever temperature that is. Now if this is 15, that line is 20, 25, 30. I thought that was about 32. So the total temperature rise is 32 minus 15, which is 17 degrees Celsius. Then it says the moles of sodium hydroxide. Have a look at this now. See if you can work out the moles of sodium hydroxide. We have plastic beaker weighs 8. Plastic beaker and distilled water is 108.15. When we add the sodium hydroxide, it goes up to 114.35. I will tell you the RMM of sodium hydroxide is 40. The RMM of sodium hydroxide is 40. So we would take the 108.15 away from 114.35 and we would get a mass of 6.2. Moles is grams over RMM. 6.2 divided by 40. 0.155. 0.155. Don't worry if you're not following this at the moment. We will go through it again. Then it says, use your results to determine the molar enthalpy solution of sodium hydroxide. Well, we've worked out Q. We work out the mass of water first is here. Take the mass of water and the mass of the plastic beaker away from the plastic beaker and water. So it's 108.15 minus 8. And that gives me 100.15. The total temperature change and the specific heat capacity, that's MC delta T, is 100.15 times 4.18 times 17, which we just got from the graph, which is 7,117, or 7.116 or 7.117 it should be, kilojoules. So then we divide that by 0.155, Q over N, and that gives me 7.117 divided by 0.155, 45.9. 45.9. And it will be negative because it is given out. Okay, now this looks very hard. I think this looks very hard. And in an examination, you would get about 10 minutes to do the whole question. So what we're going to do is bit by bit, we are going to do some examination questions, even when we are doing moles or we are doing nitrogen chemistry, we are going to suddenly put in a question on something different. So plot the graph, extrapolate, find the delta T, then work out the mass of sodium hydroxide, the moles, the mass of water, and then Q, and then divide Q by N. Okay. I thought we would finish by using some bendo-mexo calculations, just so you can see that you can still do things. So I'm going to put something on my other board, and I'm going to ask you to have a go at it. We have just 10 minutes left, so we're going to revise bendo-mexo. So we're going to see if we can do a particular calculation. I'm going to tell you the values. I'm going to change to my other camera here. If you remember, bendo-mexo was the way that we did these calculations. bendomexo stood for, was a way of remembering that breaking bonds is endothermic and therefore plus, and making bonds is exothermic and therefore negative. Sorry, I'll just put that up a little bit. There, bendomexo. So what we're going to do is we're going to just look at how to simplify these a little bit. So we're going to look at, if I take some ethene, and I add hydrogen to it, and it becomes ethane. Okay, so that's the equation, that's the picture which you need. This is a reminder of how to do bendomexo. I'm sorry, there's a bit of reflection. I'll just try and get rid of that. Hopefully that's a little bit easier to see. Still not great. Oh well. Okay, I'm going to tell you what each bond is worth. So a carbon to carbon double bond is worth 614, and a carbon to carbon single bond is worth 347. A carbon to hydrogen bond is worth 413. And a hydrogen to hydrogen bond is worth 436. Now, the important thing about this is realizing that some of these bonds do not need breaking. Okay? So you could say, okay, I'm not going to, normally we say, I'm going to break all of these bonds and then I'm going to make all of these ones. So all of these will be plus and all of those will be minus, negative, and then we will add them together. But this carbon to hydrogen bond here does not change, it's here. So I could say, look, that one there is the same as that one there. So I don't need to include it. In fact, that one, and this one, and that one, and this one, those four are all the same over here. So I don't need to include those. So sometimes it's easier to simplify. Okay, so over here, I'm not going to bother breaking these. I'm only going to break the double bond, which is worth 614, and the hydrogen to hydrogen, which is worth 436. And that all together will be bendo, that's breaking, so it's endothermic. Over here, I am going to make a carbon to carbon single bond and two carbon to hydrogen bonds here. So I'm going to add a 347 to two 413s. And this all over here, the total of this over here will be minus, will be negative. And then I total them. So have a go at that. This is just a reminder, just so you can see what you're trying to do. I'll just lower it just a bit so you can see the bottom of everything. Hello? Hello, somebody said something? See if you can have a go at that. It's just a bit of revision. Look, the four carbon to hydrogen bonds are the same in both molecules, so I'm ignoring the orange ones. So I'm looking at breaking the carbon to carbon double bond, and the hydrogen to hydrogen single bond, and then I'm making the carbon to carbon single bond and 2 carbon to hydrogen single bonds. I'm not going to break these ones. I'm not going to bother because I can simplify it. Okay? So see if you can work that out. And then see if you can show me the answer. This is revision. This is looking at the things which we have done before. So we total what we break, and then we total what we make, and all the breaking is positive, all the making is negative, and we add them together. So carbon to carbon double bond is worth 614, carbon to carbon single bond 347, carbon to hydrogen, doesn't matter where it is worth 413, and a hydrogen to hydrogen here is 436. Somebody see if they can get me an answer. Show me that again, Dandara. Not quite. You've missed out. You've missed out the hydrogen to hydrogen single and the 2 carbon to hydrogens. You've dealt with the oh, hang on. 1463. Not quite, Glory. Not quite. Nearly. Hold it still, Dandora, please. If you're going to show me the calculator, you have to hold it very still. Wamuini, the calculator box is very entertaining, but not very useful. Okay, I'm going to go back to my other camera and I'm going to talk you through it. Oh, no, not quite, Dandura. Okay, we could break everything on the left-hand side, right? Oh, very, very close, Wamuini. Very, very close. We could break everything on the left-hand side. So I could break, I'll show you on that other camera, I could break, if I was going to total all of it, I could break the carbon to carbon double bond, that would be worth 614. I could break 1, 2, 3, 4 carbon to hydrogen bonds, that's 413 each. I could break the hydrogen, that's 436. So I could break all of that and that will come to 2000 something. Or I can just spot the bits which are not going to change. So this carbon is going to, over there, that carbon is still going to be attached to 2 hydrogens there. So I'm going to ignore that. I'm not going to bother breaking it here and making it there because it's going to be the same amount. If each one of these is 413, then to break 2 of them will be 826, and then I make them over there 826. It's like having the same number on both sides of an equation. I can ignore it. So I am ignoring 1, 2, 3, 4 bonds here because they are the same over here. So I'm going to ignore them. So the only bonds I'm going to break are this one here and this one there. Okay? Those are the only two I'm going to break. So I'm going to add 614 to 436. Easy. Over here, the only ones I'm going to make are this one here, because I've broken that one. I'm going to make a new one, and I'm going to make the carbon, the new hydrogen one here, and the new carbon hydrogen one here. So I'm going to add 347 to one of those and another of those. Each one is worth 413. So each one of those is 413. So 347 and 413 and 413, and it's all going to be negative. Then I'm going to add these two numbers together, and the answer will be about negative just over 100. I'll just make it more obvious again. I'll just get rid of this and write it out again so it's clean. Now, I'm going to show you the ones I'm going to break and make. So this one I will break, that one I will break. These ones I'm going to keep exactly the same here. Okay? In this molecule here, the green ones are being broken. Over here, that one is going to be made, that one is going to be made, this one is going to be made. To break this one is 614. To break this one, the hydrogen to hydrogen, is 436. So they add together. Over here, the C single bond C is worth 347. And then I have 1, 2 times the value of each carbon to hydrogen, which is 413. And all of this together will be negative. All of this here will be positive. See if you can complete that. Really good. Mathari. The Mathari are the champions. Who is that, please? Well done, Mathari Mix. That's great. Who is that? Well done, Dandora. Who is that? Dandora. Glory. Show me. Sorry, there's a bit of reflection off it. Can I have another look? Well done, Wamuini. Well done. Very good. Well done. Well done, Joki. Well done. That's really great. Fantastic. I'm really impressed. Most people are getting the right answer. King. Yeah. Ah, I love that people give themselves a title. It's really good. Okay. If you do, well done, Glory. Very, very good. Who is that, Glory, please? I'm really pleased. Okay. John De, well done. Very, very good. Okay. It's basically the end of the lesson. Um, I know that some of you, yes, King Brown. Yes, I know King Brown. Excellent. I can't read it. I can't read that, Glory. I'm really sorry, but I can't read it because it's all fuzzy. Anyway, it doesn't matter. Um, thank you, King Brown. Okay, guys. So the answer is -123. If you got the right answer, you're fantastic. Did you get the right answer? Did you get -123? Who got -123? God, I'm so impressed. Well done, Silver Spring, even if you support Liverpool. Well done, Glory. Well done, Genesis Joy. It's very good. Well done, Wamwini. I'm really pleased. Well done. Well done, Mathari, who were first in. It is time to go, and I will wave bye-bye and say Asante Sana and Kwaheri, and I will see you again next week. Next week we will do some mole concept because I can see that some of you are not very confident, but thank you very much indeed for being here today. So I will say goodbye, bye-bye, and I will stop the recording